In this lesson, we will examine the properties of the various fuels used in aircraft engines. Aircraft piston engines use gasoline and gas turbine engines kerosene. Both of these fuels are produced from crude oil. In simple terms, the required fuel is extracted from the crude oil by a distillation process. The oil is boiled in a furnace, and then the oil vapor is cooled in a distillation column. The various hydrocarbons in the oil all have different boiling points, so they condense out of the vapor and are tapped off at different points in the column. The heavy oils condense out first and are collected near the bottom. The process then continues up through the tower, with kerosene and gasoline, which are relatively light and volatile, being taken out near the top. The specification for an ideal fuel for either a gas turbine engine or a piston engine include the following main requirements. It should flow easily under all operating conditions. It should have complete combustion under all conditions. It needs to have a high calorific value. The calorific value is a measure of the amount of heat released during its combustion. It is measured in British thermal units per pound or kilojoules per kilogram. It should be non-corrosive. There should be no damage to the engine from combustion byproducts. The fuel should present a low fire hazard. Engines should start easily. And the fuel must be able to lubricate the moving parts of the fuel pumps and other components in the system. In practice, the cost of satisfying all these criteria is prohibitive, and therefore compromises have to be made. Piston-engined aircraft use gasoline fuels grouped under the title aviation gasoline or avgas. Aviation gasoline is manufactured to conform with the exacting specifications that are issued in the United Kingdom by the UK Aviation Fuels Committee on behalf of the Defence Material Standardisation Committee. The specification number for gasoline is Defence Standard, or DEFSTAN 91-90. Aviation gasoline is graded by octane rating. The octane rating of a fuel is a measure of the fuel's resistance to detonation when subjected to high temperature and pressure. A fuel's octane rating is checked in a test engine with the fuel-air mixture weak and with it rich. This gives the fuel 2 octane ratings. The weak figure is used in the fuel's name. So for instance, Avgas 100 is a 100 octane fuel when the mixture is weak, but a 130 octane when the mixture is rich. These 2 octane ratings are known together as the fuel's performance number or index, so Avgas 100 has a performance index of 100-130. High-performance engines with high compression ratios require high-octane fuel. Engines with lower compression ratios can use lower-octane fuel. The grades of aviation gasoline currently authorized and available are Avgas 100 and Avgas 100LL. Avgas has a freezing point in the region of -58 degrees Celsius and a flash point, which is the temperature at which the fuel vapor will ignite in contact with a flame, of -40 degrees Celsius or colder. It has a specific gravity of 0.72 at 15 degrees Celsius. Specific gravity is important, as fuel is delivered by volume. but pilots need to know its mass or weight, as the energy available from the fuel is dependent on its mass, not its volume. Avgas 100 is coloured green and has a performance number of 100-130. Avgas 100LL has the same performance number as Avgas 100, but it has a lower lead content. It is coloured blue. MoGas, or motor gasoline, can sometimes be used in certain airframe engine combinations, but only under the conditions specified in Civil Aviation Authority Airworthiness Notices No. 98, 98A, 98B and 98C. Because of the higher volatility and water content of MoGas, carburetor icing and vapour locking are much more likely to occur if this fuel is used. The subjects of carburetor icing and vapour locking are covered in detail in the piston engine series of lessons. Information and advice on the use of MoGas can be found in the CAA Safety Sense Leaflet No. 4B. Diesel piston engines use AVTER. This fuel is described in the gas turbine engine fuel section. Gas turbine engined aircraft use kerosene fuels. These are heavier and less volatile than gasoline fuels. They are placed between gasoline and diesel fuel in the distillation process. The two main types of gas turbine fuel in use in civilian aircraft are aviation turbine fuel, or AVTER, and aviation turbine gasoline, or AVTAG. As with aviation gasoline, in the United Kingdom, the specifications for these fuels are issued by the UK Aviation Fuels Committee on behalf of the Defence Material Standardisation Committee. There are two grades of AVTER in use. Jet A1 is used in Europe and most of the rest of the world, whilst Jet A is used in the United States of America. Jet A1 is a kerosene-type fuel with a nominal specific gravity of 0.8 at 15 degrees Celsius. It has a flash point of 38.7 degrees Celsius and a waxing point of minus 50 degrees Celsius. Waxing is explained later in the lesson. Jet A is a similar type of fuel to Jet A1, but it has a waxing point of minus 40 degrees Celsius. Gas turbine fuels are not dyed for identification. They retain their natural colour, which can range between what is termed as water clear to a straw yellow. AVTAG is known in civil aviation as Jet B. It is not generally used in civilian aircraft. It is a gasoline and kerosene mix with a nominal specific gravity of 0.77 at 15 degrees Celsius. It has a flash point of minus 20 degrees and a waxing point of minus 60 degrees Celsius. Because of the very low waxing point, it may be found in use at a small number of civil airfields in very cold climates. If a fuel sample is placed in a clear glass container and swirled vigorously, and the sample appears cloudy or hazy, then there could be one of two reasons for this. If the cloudiness appears to rise quite rapidly towards the top of the sample, then air is present. But if the cloud falls quite slowly towards the bottom of the sample, then water is present in the fuel. Having said that, a cloudy appearance usually indicates the presence of water. A certain amount of water is present in all fuel. The water, which is dissolved in the fuel, gives rise to a number of fuel system problems. As an aircraft climbs to altitude, the fuel is cooled and the amount of dissolved water it can hold is reduced. Water droplets form, and as the temperature is further reduced, the droplets turn to ice crystals, which can block fuel system components such as filters. A microbiological fungus called Cladosporium resinae is present in all turbine fuels. This fungus grows rapidly in the presence of water to form long green filaments which can block fuel system components. The waste products of the fungus are corrosive, especially to fuel tank sealing substances. The inclusion of a fuel system icing inhibitor, or FSII, in the fuel will help to overcome these problems. The inhibitor in common use inhibits the ability of the water in the fuel to freeze and acts as a pesticide which retards the growth of the fungus in the fuel. Jet A1 has FSII, but Jet A does not. As we have already said, water is always present in fuel. The amount will vary according to the efficiency of the manufacturer's quality control and the preventative measures taken during storage and transfer. Further measures can be taken to minimize water accretion once the fuel has been transferred to the aircraft tanks. If the fuel can be allowed to settle after replenishment, then the water droplets, being heavier than the fuel, will fall to the bottom of the tank and can then be drained off through the water drain valve, which is situated in a sump in the lowest part of the fuel tank. Once the fuel is in the aircraft tanks, the main source of water contamination is the atmosphere that remains within the tank. If the tanks are topped up to full, then the atmosphere is excluded together with the moisture it contains, thus minimizing the likelihood that fuel will be contaminated. Caution is required here. Filling up the tanks may prove an embarrassment later if the ambient temperature rises, as the fuel in the tanks will expand, and there is a danger it may spill out of the vent system. Filling the fuel tanks may also incur a performance penalty, as the aircraft may be too heavy to take off with the required passenger or cargo load, and some fuel may have to be removed. As a further precaution, in order to prevent any ice crystals blocking fuel filters and jets, the fuel may be passed through a fuel heater located on the engine, which uses hot air from the engine compressor to remove any ice crystals which may have formed in the fuel when it's cooler than 0 degrees Celsius. Some systems utilize a fuel-cooled oil cooler as well as or instead of a fuel heater. The fuel-cooled oil cooler uses the hot engine oil to warm the fuel and in doing so produces the added benefit of cooling the oil. A number of additives may be blended into the fuel either at the refinery or the airfield to improve the operating ability of the fuel. A lubricity agent is added to the fuel to reduce wear in moving parts of the fuel system components. Static dissipator additives partially eliminate the hazards of static electricity generated by the movement of fuel through modern fuel transfer systems. This would otherwise be a particular problem with the high flow rates generated during refueling and defueling. Corrosion inhibitors protect ferrous metals in fuel handling systems, such as pipelines and storage tanks, from corrosion. Certain of these corrosion inhibitors improve the lubricating qualities of some gas turbine engine fuels. Metal deactivators suppress the tendency, which some metals, particularly copper, have, to cause the fuel to oxidize. We are now going to talk about fuel waxing. This is something that happens to fuel when it is extremely cold. Do not confuse this with the water in the fuel freezing. Gas turbine fuel consists of many hydrocarbons, each with its own freezing point, so it doesn't become a solid at one temperature in the same way that water does. As the temperature of the fuel drops, the heavy hydrocarbons, which have the highest freezing point, freeze first and form wax crystals. As the temperature drops further, the hydrocarbons with slightly lower freezing points start to solidify, and so on as the temperature continues to fall. The waxing point of a fuel is the temperature at which wax crystals begin to form. Jet A1 has a waxing point of -50 degrees Celsius, so waxing is only a problem for aircraft operating for prolonged periods at high altitude in very low temperatures. The crystals can clog the fuel filter and interfere with the operation of the engine fuel control unit. The effects of waxing can be minimized by the refinery keeping the heavy hydrocarbons in the fuel to a low level. The temperature at which a liquid boils will reduce as the pressure on its surface reduces. As an aircraft climbs, the pressure on the surface of the fuel reduces, and with that reduction comes an increased likelihood that the fuel will boil and form vapor in the pipelines. The vapor locks that this effect causes can cut off the fuel supply to the engine, with the result that the engine will stop. Fuel booster pumps fitted inside the tanks can help to overcome this problem by pressurizing the fuel in the pipelines from the tank to the engine, pushing fuel towards the engine rather than engine-driven pumps sucking fuel from the tanks and further reducing the pressure. Specific gravity, or SG, is defined as the ratio of the density of a given solid or liquid substance to the density of water. Or, to put it more simply, it is the weight or mass of the liquid divided by the weight or mass of an equal volume of water. So in the example shown here, we have 1 gallon of fuel in the left container, and it weighs 8 pounds. In the right container, there is an equal volume, 1 gallon of water, and it weighs 10 pounds. The specific gravity of the fuel is then 8 divided by 10, or 0.8. Specific gravity has no dimensions. The higher the specific gravity of a fuel, the greater will be the mass or weight of fuel for a given volume. And conversely, the lower the specific gravity, the less will be the mass or weight for any given volume. The specific gravity of fuel varies inversely with its temperature, so, depending on the storage conditions, the specific gravity of the fuel supplied to an aircraft may be different from the standard value. On modern aircraft fuel systems, this usually makes little difference, as fuel in the aircraft tanks is measured in mass or weight rather than volume, with the fuel quantity measuring system compensating for changes in fuel-specific gravity. However, if a high fuel load is required, it may not be possible to get sufficient volume of fuel on board for the required mass if the specific gravity of the fuel is low. That is the end of the lesson. The tables listing the characteristics of the various fuel types are shown on screen. Remember that ice crystals formed from water in the fuel are prevented from blocking the fuel filter by heating the fuel upstream of the filter using either hot air or oil.